Hello, Chem 1 class. I'm going to go over the Chapter 6 study guide now. So what you're seeing right now on your screen is Chapter 6 study guide, so I guess I'll just go ahead and get to work. Let me go ahead and snip this bad boy. Okay, so what you're looking at, it says the wavelength of radiation that has a frequency of 6.912 times 10 to the 14 reciprocal seconds or hertz. And of course, they give you the frequency. They want you to find the wavelength. I even gave you the equation right here. All you got to do is plug. So let's go ahead and do that. I think I'll go ahead and do my algebraic manipulation first. I'm going to say the wavelength is equal to c divided by nu. So the wavelength is equal to 3.00 times 10 to the 8 meters per second divided by the frequency, which is 6.912 times 10 to the 14 reciprocal seconds. Notice I have reciprocal seconds in the numerator and the denominator. They cancel each other out. The only unit I'm left with, of course, is going to be meters. So I'm going to take 3 times 10 to the 8 divided into 6.912 times 10 to the 14. I get 6.34 times 10 to the negative 7 meters. Now this is the wavelength in meters, but of course the answers there are in nanometers. So of course let's go ahead and convert it to nanometers on your exam. Of course, I'm not going to ask you to do that. I'm just going to ask you to give me the answer in meters and just be done with it. Well, probably. I shouldn't say that. Yeah, probably. That's probably the case. But we know that 1 times 10 to the 9 nanometers is equal to 1 meter. Or I could also say 1 times 10 to the negative 9 meters is equal to 1 nanometer. Both of these are equally valid. So of course I'm going to go ahead and use either one of them. I think I'll use the first one. Nanometers and meters. Of course, you're going to multiply it by a conversion factor fraction. And I don't know why I'm getting my calculator. It's obvious. 9 minus 7 is 2. So it's going to be 4.34 times 10 to the 2 nanometers, which is equal to 434 nanometers. I'm pretty sure that's violet light. So the answer there is B. All right, B. All right. So let's go ahead and take a look at number 2. What is the wavelength of radiation that has a frequency of 2.10 times 10 to the 14? So number 2 is just like number 1. So of course you can go ahead and do that. I won't bother doing that one. Number 3, calculate the energy of a photon with a frequency of 6.17 times 10 to the 14 reciprocal centimeters or hertz. Let's go ahead and snip that bad boy. Alrighty then. Now, of course, since they're giving you a frequency and they want you to find the energy, I'm going to use this. E is equal to Planck's constant times the frequency. So, of course, that being the case, and since I'm trying to find energy, all I have to do is plug in Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. And that, of course, is going to be multiplied by the frequency, which is 6.17 times 10 to the 14 reciprocal seconds. cycles per second, or hertz. Now notice I have reciprocal seconds in the numerator, and I also have seconds in the numerator. They cancel out, don't they? So what I'm left with is units of joules. So when I take 6.626 times 10 to the negative 34, multiply that times 6.17 times 10 to the 14, I get 4.088 times 10 to the negative 19 joules. Okay, yeah. So, yeah, that's the answer. So, of course, it's good to 3 significant digits. So, you round that 8 up to a 9. So, it's 4.09 times 10 to the negative 19. So, the answer is number 4. I mean, C. 4.09 times 10 to the negative 19. So, going back to, let's see what. Now, number 5 is, it has the energy in joules of 1 photon of microwave radiation. With a wavelength of 0.122 meters. Okay, and they give you this nice fancy equation relating energy of a photon to the wavelength of said photon. So let's see what we have here. So of course, since we're trying to find energy, we don't have to do any algebraic manipulation. Just plug in variables. 6.626 times 10 to the negative 34 joules times seconds. 3.00 times 10 to the 8 meters per second. No. And the wavelength was 0.122 meters. A very, very, very long wavelength. That might be in, I don't know, that might be the microwave region of the spectrum. Okay, well. Now, of course, I have meters in my numerator of the speed of light and meters in the denominator of wavelength. They cancel out. I have also reciprocal seconds in the speed of light and seconds in Planck's constant. They cancel out. The only unit I'm left with is, of course, joules, which is, since I'm trying to find energy, that makes sense. So 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided into 0.122. You end up getting 1.629 times 10 to the negative 24 joules. And let's see what that corresponds to. It's good to 3 significant digits, so it would be 1.63 times 10 to the negative 24 joules. And that would be C again. So the answer for that one is also C. Okay. So let's see. Let's see. Now, 6 is similar, but they ask you to find the energy associated with a mole of photons. Okay, a mole of photons. They give us a lot to work with here. Not only do they give us Planck's constant and the speed of light, but they also give us Avogadro's number. So let's go ahead and take a gander at this problem after I snip it. Okay, so what we have right here. Now again, I'm going to go ahead and find the energy. This should be no problem finding the energy associated with 1 photon. 6.626 times 10 to the negative 34 joules times seconds. That's Planck's constant. That's my H. Then I'm going to put the speed of light, 3.00 times 10 to the 8 meters per second, divided by the wavelength, which is, well, now 486 nanometers. You do need to convert that to meters. So, of course, 486 nanometers times Uh, let's see. So I'm going to say 1 meter divided by 1 times 10 to the 9 nanometers. Of course, that's 4.86 times 10 to the 2 nanometers. So that's going to be 2 minus 9. That's going to be -7. So that's 4.86 times 10 to the -7 meters. And let's see. 4.86 times 10 to the -7 meters. Put that right there for wavelength. Now, of course, I have meters in the denominator and meters in the numerator. They cancel out. I have reciprocal seconds. And I'm going to, of course, go ahead and find the energy. So energy is equal to, I'm going to take 6.626 times 10 to the -34 times 3 exponent 8 divided into 4.86 times 10 to the -7. That is, what the hell is that? 4.09 times 10 to the -19 joules. Okay, now what I'm going to do right here is I'm going to say, since this is the energy per photon, I'm going to say joules per photon. Okay, all right, because we want to cancel that out. And now I get to use Avogadro's number, because remember, a mole is 6.022 times 10 to the 23rd of anything. So in this case, I'm going to say photons. So I'm going to say 6.022 times 10 to the 23rd photons per mole. Okay. Now, of course, photons cancel out, and I'm going to be left with joules per mole. So 4.09 times 10 to the -19 times 6.022 times 10 to the 23rd. So the answer is 2.46 times 10 to the 5 joules per mole. Okay, so let's see what that corresponds to. Let's see. That would be 246 kilojoules, wouldn't it? Because yeah, if you convert joules to kilojoules, you'd have to, of course, divide by 1,000, or take 3 away from that exponent. So that'd be 2.46 times 10 to the 2, and that's the same as saying 246. So the answer, of course, is E. Now let's see if we can do number 7. Complete this sentence. Atoms emit visible and ultraviolet light as electrons jump from a lower energy state to a higher energy state. Of course, if they do that, go from lower to higher, they have to absorb energy, not emit it. B, as the atoms condense from a gas to a liquid. No, that has nothing to do with emission of light. C, as electrons jump from higher energy to a lower energy. Yeah, so that's C. That's the right answer. Of course, is C. All right. So, of course, if we go from higher energy to lower energy, we know we can't destroy energy according to this first law of thermodynamics. So it can emit that energy in the form of light. Okay. Now, of course, it's not going to be D, as they are heated and the solid melts to form a liquid. No. And E, as the electrons move about the atom within an orbit. No. Okay. 8. Calculate the energy in joules required to excite a hydrogen atom by causing an electronic transition from the n equals 1 to the n equals 4 principal energy level. Okay. Recall that the Rydberg equation is. So I have everything you need right here. All right. I gave you the Rydberg equation. All right. So we have, now let's go ahead and snip this bad Using this Rydberg equation is actually pretty darn simple. Okay, it's pretty darn simple. All right, so let's go ahead and use that bad boy. Sub L can also equal to 1, because remember, when L is equal to 1, M sub L can equal to -1, 0, or 1. So B, we can't exclude B. So let's see, N can equal to 5. When N is equal to 5, L can equal to 4. When L is equal to 4, M sub L can equal to -4. So that's allowed 2. N is equal to 2, L can equal to 1. When L is equal to 1, M sub L cannot equal to -3. So the answer is D. Okay. Now the only other quantum number they didn't put up here was M sub S. So M sub S, you guys just remember, can either equal +1/2 or a -1/2. Okay. All right, so number 10, which one of the following sets of quantum numbers is not possible? Let me go ahead and go through this rather quickly. It's not row 1. It's row 2, isn't it? So N can equal to 3, and when N is equal to 3, L can equal to 0, but when L is equal to 0, M sub L cannot equal to 1. It can only equal to 0. Okay, so row 2 is the one that's the oddball out, and of course, all of my M sub S values are allowed for all 5 rows. So the answer there would be B, row, because it corresponds to row 2. Number 11 says, which one of the following sets of quantum numbers is not possible? And let's see what we have right here. Again, it's row 2, isn't it? If L is equal to 2, M sub L cannot equal to -3. Remember, M